then projecting forward to the post-digital, it might not seem so brave, but I will try. I want to start by giving you a sense, because I'm going to probably diverge from what we think about the core discipline of architecture, and certainly diverge from how those of you who are students who know me from teaching in projections or design principles know me. I want to just frame like my research agenda broadly, so that when we diverge, you can understand the context for that diverging. So super broadly, I think the status quo is computation is a bunch of digital tools, and digital tools can be problematic in many ways, but predominantly because they presume an agenda or an answer or a task that's supposed to be solved. It makes them a kind of instrument. The goal, right, this is implicit, something we say all the time, is digital media. Digital media is something where in that realm, questions can be raised, right? The content and the environment can push back to a certain extent. So a related question is, how do we break open digital media in order to do computation, right? So we have digital media, but so what? And the so what for me lies in the inside computation. There are actions, logics, relationships, structures that have meaning for architecture, and it takes some doing to strip away the kind of layers of interface and software which amount to someone else's agenda, right, to get at the core of computation. A related question is, who's the author? Is the person who wrote the software the author of what you're making, or are you the author? What happens when we, as architects, make software for someone else to use? Is that a situation of co-authorship? And when we're not 100% the author, who's in control? And is 100% control, does that go against the idea of the first question? Is how do we make a digital media, right? Does control negate things like surprise or the serendipitous discovery? And I've spent a lot of time thinking about these questions about computation, and I care about how computation is an inherently architectural problem. How architects might approach computation or confront computation differently than a computer scientist, or for that matter, differently than an engineer or a mathematician. This is a pursuit of the core questions of computation and the core questions of architecture meeting. And lastly, what's the role of computation outside of automation or simulation? This is very much related to the other questions, but if computation only exists as a kind of something extra, a kind of way that we would do what we've always done a little bit better or a little bit more efficiently, or we can see or experience something just with a little bit more detail, a little bit more fidelity than what we already had. To me, that doesn't sort of lead to computation being a research agenda or being a kind of theory that should influence how we might do something in an advanced or even a core studio. So that's the background. I want to take a moment now to unpack the title, pre-digital to post-digital, and I want to do that by first talking about the last time I heard, or the most recent time, pre-digital got in my mind. And I owe somebody at MIT named William O'Brien, who taught, I assisted him in teaching a studio called it was about the map building to some extent, but the map building and post-digital figurations. So William O'Brien is not the first person to say pre-digital, he implies pre-digital by saying post-digital, but he's certainly not the first person to say either. I did this the other night. Don't try it at home, but you can Google search post-digital. You get a lot of hyper-digital. But what William O'Brien's research agenda is looking at post-digital figurations, forms and formal systems that move beyond what was architecture's digital project. So this presupposes a digital middle ground where there were certain types of projects interpret certain types of formal considerations that could only exist because of digital media. And the thesis of those projects was carried forward and extended to specifically address digital media. And here are just some examples of what I think of when I think of the purely digital project. You probably have some others. And this is precisely the segment of computing history that I'm not going to talk about today. I'm going to talk about the before this and what could potentially happen after this. And I find these projects canonical and important, and they're in something like a post-digital studio. They need to be referenced regularly. They often have to do things with things like a continuous surface. Our president dabbled in the post-digital. He had an exhibition and corresponding publication called The Post-Digital, which took place in 2001. And as a graphic designer, computer scientist, and artist, he'll help us segue away from architecture as needed to talk about the post-digital. And I think, I would like to read a quote from this because it sets the stage for, I'll read. The common acceptance of the term computer user to describe such daily interaction hides a fundamental question. Are we using the computers, or are the computers using us? In the complex, infinite loops of today's highly interactive software, how far could a computer go without us? Constant tending to its incessant needs to conform, or its matter of being. And then later, in a kind of closing argument about the state of digital media as a research agenda today, he concludes, there are many routes left to explore. However, most recently I have had the disturbing sense that no matter the new digital territory may arise, we end up where we first began, back into the infinite loop. My instinctive response to this personal perception has been to proclaim a new effort to escape to the post-digital, which, although post implies the future, I am certain lies in the past. That slide was meant to be on while I was reading this, but should I read it again? No. So I think I might have actually slipped when I was practicing this lecture. I sometimes would say pre-digital when I meant post-digital, and so if I already did that once, I'm sorry. But they kind of conflate, and the kind of trajectory that I noted in my own research about what might be the computational questions beyond digital media took me back to the past automatically. So to find this essay and this sort of made as way of framing the next steps of post-digital culture also relating to the past, I think taps into a kind of pervasive trend of looking back to the roots of computation, of proto-digital media, to help us move forward. So unlike William O'Brien, that's looking for a post-digital figuration, post-digital forms, which is a very interesting, provocative, long, and open-ended question, I'd like to take a little divergent approach, which is to focus on what is a post-digital process. And to me, that gets to the idea of focusing on the computing drawing. One of the ways that the layers of software and the kind of packing digital media with application-specific agendas kind of has to do with building complex and rich and layered models of buildings. So I have found it productive to step back away from all of that for a period of time and focus on the computed drawing. And you can take computing drawing to mean two things. Computing in order to generate a drawing, but also computing by doing drawing, which is something that architects did. If you ask where did computing start, this is an interesting question, not meant to be the subject of this lecture, but I'll indulge myself in this tangent. If you ask an architect or if you ask a sociologist where computing started, she might say it started in the roots of language, where as soon as we can abstract an idea or structure it in an indirect way, we were already doing computation. And to make a language functional, it has to have a coherent logical system to make a grammar. If you asked a computer scientist, she might say computing started with arithmetic symbols, right? The counting and doing operations, things like numerals or something like an abacus was the start. Of course, you might ask another computer scientist and they would make point to like an analog computer, anything that could store information or solve problems or do a kind of multi-step algorithm. But an architect, I think, would say the origins of computing are the marking of lines that mean more than just the ink or the tone or the graphite on the paper. The line is not just a matter, it has a representational connotation. It means or it could mean an edge, a boundary, it could mean a thing. But by making that line, and this is why so many architects, sometimes it's hard to explain to non-architects, put so much emphasis on the sketch as a way of thinking, right? It's not just recording ideas to communicate with someone else, but there's resolving problems in the drawing. So I'm interested in focusing on the drawing. So throughout the lecture, when I cite something, I'll try to make a big bibliographic slide, so if you're in the video or the internet and watching this, you can find the further reading. Here's the second thing I want to read. This is John Fraser is credited with doing the first architectural project at a school of architecture, an architectural degree program with the computer. So this is something rare in the 60s. He ended up developing a whole thread of computation research throughout his career. Most recently, he was the director of, I might get this wrong, international research at Gary Technologies. This is his quote. So it became a challenge of computing without computers. Like an athlete prepares mentally by rehearsing in the imagination the achievement of some difficult feat. In architecture, we spent the 60s and 70s going through a mental rehearsal of what it would be like at the beginning of the 21st century, except we were thinking it would all happen in the 80s. I enrolled at the Independent Architectural Association in '63. My own experience was a typical struggle against both the lack of computers and some hostile staff attitudes to computing. For example, in 1964, I was ridiculed for designing a church based on a series of Boolean diagrams representing the relationships between theological propositions. The reality was that the AA only acquired a teletype terminal to a time-sharing mainframe in 1967, and no computing instruction was available. So I went to the London School of Economics to learn programming, discovering how to program in Fortran using punched cards for the data analysis of social surveys. Later, I had to cross a vast gap from writing code to count single-parent families to programming the instructions for drawing buildings. The next lesson came The next lesson came in 1967, or the academic year 67-68, through the pain of generating my first computer drawings plotted in black ink on cartridge paper. Creating drawings of a geometrical complexity that was virtually impossible by hand was inspirational. But the agony of writing software, there was no AutoCAD, and entering all that data started me on a lifelong project to improve the situation. I produced my final year drawings using paper tape as the input and outputting from a flatbed plotter that I had to hire by the hour. With no screen preview, there was every chance that the drawing would be blank. But there was great joy whenever the pen began its painstaking plotting. At last, I had finished what was possibly the first student project to be fully drawn by computer, and won the year prize for it, only to have the original drawings stolen from the end of the year exhibition. So I will shift now to looking at that same period that Fraser is talking about. I think he sets the stage for an environment that is not surprising. Architecture is lagging behind other disciplines in using using computers. This is not to say that architecture should be critiqued for that necessarily. Investing in a computer was a huge endeavor, and this is the time when computers took floors of buildings. So it's no surprise that he had to go outside of the department to learn computing, and no surprise that it was strange and horrifying for those in architecture to wrap their heads around using the computer to indirectly produce drawings. He also talks about some really interesting things about the faculty who eventually did accept the computer. They began to use or demand that drawings, their sketches would be translated into the plotter for output, but did not respect the authorship role of that translation. Right? So these questions that I posed at the beginning, these sort of important research questions of today, they were equally apparent, or even more viscerally apparent, in the 60s. So this is one of two publications that is attached to an exhibit about, or attached to an exhibit and a set of historical research about the computer's arrival in the fine art world. So the fine art world, we know in many ways is allied with architecture, but it's, it's not to say that the fine art world was any more accepting necessarily of computation. In this book, Deborah Wood quotes this awesome response letter to a enterprising art critic who is submitting a proposal to write an essay in something like Art Forum, and her response is something, his or her response is something along the lines of, I cannot even fathom an art magazine or art journal ever doing an article on the computer for art. So, as absurd as that sounds now, digital art we take for granted as a discipline, but it was quite a strange and messy territory that has been fascinating for me to study. So this book and this exhibit, the historical computer print, really does, and a lot of the images I'm about to show are taken. Some of them are taken from this exhibition. There's a great introductory essay. This likewise is a very good publication about specifically a movement and series of themed exhibitions that began in Croatia and traveled around Southern Europe in the art scene that began slightly before computation, was friendly towards computing, became curious about computing, welcomed scientists who were shifting from doing computing to solve scientific problems or further scientific research to translate back into art. So I highly recommend both of these texts for anyone who is interested in further reading. So here we are, the first digital art. Leposky is a scientist. He gradually begins to artfully represent and frame the waveforms that are the result of his research. Right? So he is a member of this exhibition, and there's a smooth transition from he's found these waveforms to then constructing these waveforms, and then part of what he had to do was design a way to make them prints. Right? This is still on an oscilloscope, not a digital screen. So part of this was using photography to extend the computing apparatus, because these things were fleeting images, so they occurred over time. So capturing them and making them an image in a document was a significant and non-trivial task. But such beautiful lines, right? They get at what we care about in a drawing, the moment of marking, the duration of each line, the end that tapers versus the end that builds up higher density. Of course, they suggest three-dimensional form. So it's great to me that the first example that we have of computer art or digital art is so inherently architectural. Now, still again before the use of the computer, and this is in the New Tendencies. The New Tendencies was an exhibit that started in 1961 in Croatia, and it eventually spawned a movement. And although everything in the 61 exhibit is proto-computational, right? They knew about the computer. There was a reaction to art as a commodity. So there's an interest in being ultra systematic, but no one was actually using a computer. But you get these great interactive things like these disks where by interacting with them and rotating them, you build up these other compositions. So there's a theme here of kind of being systematic to break open art as a kind of mythical and mysterious or hidden process. You get things that will look, you'll see images like this in the computer art of just a couple of years later that's made with a plotter, but in this case it's an oil painting. So very systematic, those of you that do coding in Python or processing, if you looked at this and you squinted your eyes, you would think you were looking at like a processing image, right? Because it's so tied to the grid, and you could almost like imagine the rules, right? The increased density relative to a focal point here, references to another area here, bandings that are linearly treated. So it's like this one that even shows pixels, right? I can't imagine anything more proto-digital than unitizing the element of an image to treat that as one color, even to show gradients here. Another one that was interactive, so this is just basically a drawing, a sculpture as a drawing, or a drawing with a sculptural medium. Again, interactive, those spherical objects are placed in this thing, and you can have beginning states, desired states, end states, and states in between. By the way, there's an essay or a sub-lecture just in the titles of these things. If you haven't been paying attention, rectangle. Chromatic progression in yellow, orange, and red. Electronic K25 version 2. So this again gets at the you need to develop from start to end, and oftentimes to be systematic, you had to have in your process a way to make tons of these things. So a naming convention they started to be not just indexes for things or the narrative description of things. They started to be very complex codes that talked about where this work happened in the sequence of multiple works. So in 64, we're seeing the first drawings that are output from a computer. So Michael Knoll is he participates in subsequent New Tendencies exhibitions. This one is pulled from the computer print series. He's a computer scientist who was interested in looking at modern art. So this one is particular. I think this one is not labeled, but he's looking at Mondrian in particular, noting the systems and the rules, and using that to analyzing that and using that to code an algorithm to make a very primitive microfilm plotter drawing. Some homages to artists are more explicitly labeled, as this one is. Look at the name of that one. Homage to Paul Klee, 13/9, 65, number 2. Why would a date matter? The exact date. I mean, it's certainly not conventions in the art world to cite things or to title things with the exact date that you made it. And what becomes eminently clear when you're working with, or when you were dealing with computation at this time, or when you're dealing with any kind of computer-controlled device, the device now will be different than the device one day from now, right? So the plotter the plotters, in this case there was probably a technician that might be different. The environment in the air might affect the humidity, might affect kind of the type of contact that the pen head might make with the paper. And of course, all of these things, pen plotters, deteriorate gradually. So even if on the same day, at the same time, we look at number 3, at least hypothetically, it would be different. Whether those differences would be noticeable or not would depend on the context. So here's another number 2. I don't know what number 1 looks like in this case, but imagine how exciting it must have been to have on paper things like the blue line and the orange line ending at the same spot, 2 different plotter heads at exactly the same place. Straight lines might not have been so exciting. We could have, a very skilled draftsman can draw a straight line. But the type of precision that would get their 2 overlapping lines at exactly the same place starts to be so a precision that is inhuman to the extent that it must have been fascinating and super exciting. I mean, if I'm excited in 2013 about that, I bet they were excited also. And I'm presenting all of these works in chronological order. So there's a couple of threads of interest that start to pick up only at certain times. So you can see before 65, this is the first example that I could find anyway, in which the algorithm that was used to make the drawing had a random component to it. And randomness was already kind of very important. It gets to are you designing the system and the structure in an interactive art, right? You're not designing how the specific patterns you could make with the black spheres, the black versus the white spheres in the grid. You're designing a system by which an infinite series of black, white, spherical images could be made. So that the computer could give you a random number, and that you could still make art with that random number, still control it, is, I think, a concept that is relevant still today. So this is nothing more complicated than squares in a grid. That near the top of the grid, their random rotation and random shifting is weighted more heavily. Also interesting that the title is untitled, parenthetically gravel stones. Gravel stones is not the title. There's a parenthetical reference in the title. The same artist, untitled again, starting to produce multiples, right? So there's also a random component here. In the case of these algorithms, it's, I'm pretty sure, I've studied these enough, the code is not available on these, but I'm pretty sure what happens is that there is a series of randomly generated new points that are connected with orthogonal lines. So if the previous point was here, the next point is here, across this. And there's like a 1 in 100 chance that instead of doing this, you bypass it and draw a diagonal line. That in itself is not particularly important, except for the fact that it makes these seem very, the collection is, it seems almost human. Like there was a split-second change of mind or a gestural mark that was diagonal. And there was a lot of interest in that condition in the art world, in the computing world, in the artificial intelligence world at that time. How could you make things that had characteristics of intelligence or characteristics of life or intelligence or decision-making or emotion? There was a lot of interest in things like robotics that would appear to find their way to a home. That even if you know how they work, you can't help but kind of empathize with them because of their performance. So that's interesting, number one. Also interesting is that diagonal starts to imply depth or something three-dimensional. And so as a kind of filter to look at stuff that is artistic, one of the ways I always classify things is to what extent does a 2D operation suggest or imply depth. Here's another where that spine right? A very simple, very primitive algorithm implies that this might be something like a folded surface. Again, there's an element of periodic and inconsistent randomness that occasionally makes it look like a mistake or a flaw or a deviation from the regular. Again, randomness, in this case, it's given a circle, picking two random spots on the circumference of the circle and drawing a line. You'll see also that I've started to show the medium here has started to be ink on paper. The plotters have gotten slightly larger, that there doesn't need to be a process of photographing or using some kind of chemical process to take something small, make a negative out of it, and then produce a photograph. They're starting to be large enough that the actual the artifact is able to be present. And that matters significantly because you'll start to see, well, you'll see it matter in some of the work I will show in a minute. But when you can have these drawings larger, you can see the line, and you can see the time of the line, the start of the line being different than the end of the line, the speed of the line, and even see things like the overlap of the line looking darker than any individual line segment. Charles Shurey, who had a long career in computing for visual arts and computing for graphics, taught in computing for a long time at, I believe, Carnegie Mellon. I'm going to fix all my mistakes in like the comments section of the video on the website. So this is an interesting shift because it's he's taken the step of being representational, and representational is kind of a word that I avoid at all costs when looking at this stuff, because everything is always on the cusp of potentially representing something, right? As I said, in architecture, a line always represents the geometry, and is considered in terms more broad than the medium of ink or tone. So he's taking some kind of source, though. Whether this was a photograph that he did analysis on in order to construct the sine wave equations, I'm not exactly sure, but it opens up a whole other territory of a point of reference, a figure of reference, an image of reference, and things that happen when it gets very dark, the ink bleeding, the individual lines evolving into areas of deep, dense figure. And there's like striking just the balance between this being an image made out of sine curves and an image that represents a face. Another plotter drawing, extremely simple, and again, this you can imagine when you look at I don't have the exact dimensions here, but this one is larger, right? So this one matters. This one has a big and profound effect when you can look at it, not the way we're looking at it here, which is a digital projection of a scan of a book print, which itself was a scan of the real thing. But there's a lot of exciting things happening when the lines can be read individually, creating these moire patterns, which might be an artifact of that translation, but something like that is probably visible in the print itself. Here's another important milestone. All of these have a kind of milestone, but in this one, it does something that architectural drawing and computing with architecture, or let's say like scripting with architecture, has often a very, very difficult time doing, which is the lines here. These are just lines that are built up. Probably there was a random point, and then a line that was drawn from that random point at a kind of maximal length. But the lines stop when they intersect another line. So the line is given a kind of material quality. So they're not allowed to freely overlap each other. And it means that the structure and the definition of the line has to be more advanced than saying start here and end here. There has to be a collection of things that knows all of the lines that are in that collection, And each line has to be able to, or the thing that draws the line, whatever that abstract thing is, has to be able to look at, given this start point, given this trajectory and where that line might end up, where would it intersect, find that intersection point, and draw the line only up to and not including that intersection. So it's an approach to programming that is deeper than just the sequence of operations, that it's like draw a line, draw the next line, draw the line after that. And it also means that there had to be a representation of this drawing somewhere before it got plotted. Now, that representation was not on a screen. This was before you could plot lines, at least before you could plot lines conveniently on a screen. So that representation wasn't an image that looked like this. That representation was somehow in the abstract structure of the code, something that kept track of what these lines were and where they existed. That meant that there had to be a way of storing all of this linear information in a way that would allow the later lines to reference the earlier lines. And that storage was probably, again, a really significant technical feat, because storage was one of those things that came at an extremely expensive premium in 1969. Meccano drawing 44969. So 449 is quite an intimidating number when you're versioning things. This series, you can tell by the quality of these curves, is not about drawing a primitive shape, but is setting up a couple of variables that are interrelated. So that's why the effect is something like these areas reading like gravity wells. As we move forward, now we're in 1970. In this case, the drawing is now starting to be keyed, I would think, not casually or not sort of happening on something that could be read by a really optimistic architect that says, oh, that looks like it could be depth. Here, I think the depth is inescapable, that the nature of these curves and the nature of things like a focal point starts to register as a perspective. This is particularly advanced in the sense that I've had a really hard time decoding or working in reverse to identify what the algorithm does. There's a couple of layers of things happening here that is extremely complex. Another one, less complex, but again, cued very specifically, and I would say very unavoidably, to some idea of 3 dimensions. So, I got a plotter. This is it. I got one that is not as vintage as the collector in me would have wanted. This is from the late 80s. But all pen plotters are basically obsolete. And so this one I was lucky enough to find, I have a couple of them now, but I was lucky enough to find, let me pause this, it's getting ahead of me. Lucky enough to find it in working condition. But working condition for a plotter like this means that you can turn it on, and if you send it the controls, send it commands in its proprietary language, it'll do stuff for you. It'll do what you say. That does not mean you can plug it into your computer, download the drivers off the internet, and do a file print. Not that I would want to do that, but there's something very satisfying about knowing that I couldn't do that, even if I wanted to. This is not an output device anymore. It's a programmable drawing apparatus. So it's, well, before I get into the technical logistics of it, it has a little arm. Maybe it's inappropriate to call it an arm. I call it an arm, and I call this its hand. And it has pens, a carousel of pens. I have names for them, but I will not be telling you what those names are. I think that'll make me look too, well, I guess I already made myself look strange by saying they have names. They have reasonable technical names. But, so it has eight different pens that it can pick up and draw with. And those 8 pens, will give you a range of colors and give you a range of line weights depending on the pens. The pens are there's nothing to them. You can make them yourself. All that matters is that they have to be a certain height, and it has to be at a certain point in diameter, a very narrow piece where the finger can grab onto it. But you can make your own. People have made their own. There's a there's a community of people that use the same kind of Python library, or developed the Python library that I used to help me control this, that have made their own. They come in different pen types and sizes, and for some reason they also manufacture these pens, and you can buy them because they're so cheap and basic. I was talking to someone the other day, and they asked me how easy is it to fix this, or when something breaks in a plotter, is it more daunting because there are all these intricate working parts, or is it easier? And it's much easier. Everything is, you can open it, you can see that the left and right is powered by one motor, the up and down is powered by a second motor, and even the carousel that rotates, because everything is economical, is powered by one of those motors. So even to move to grab a new pen, it has to shift the paper. So it does some very awkward movements sometimes. And you can see here, it can move very fast, and it does the instructions when you tell it to it. So it draws things in whatever order you want it to, at whatever speed you want it to. It'll leave the pen sitting there on the paper for ink to just pool out if you want it to. The sequence of kind of technologies necessary for this is here. Programming, for those of you that are interested, probably not a lot of you, but I feel obligated to say this. Pygame is a way of representing things on the screen when you want to without going into software. NumPy is a abstract library for dealing with large and complex numeric and symbolic systems in a speedy way. And Chipotle, get it? If you go to the website, you'll get it. These are the people that wrote a Python library that makes it a little bit easier to take Python code and generate this stuff. This is HPGL, Hewlett-Packard Graphics Language. This is actually what you have to send to the plotter to make it go. And it looks like horrible code, like the kind of type of code that you see, when like Neo's programming in the Matrix, like as obtuse as it could possibly get. But you can read it. There are two-letter codes, and then the information for that to execute that code, and then a semicolon. So this is select pen number 1, pen up, which means move with the pen not touching the paper to the coordinates negative 20,613.29, comma, negative 10,063.99, and then pen down, which means touch the paper and move to another point, and then without lifting lift up, go to another point. So this is, and this is a snippet of these instructions that to make a complex drawing will be vast and long. And you can sit there actually with a in terminal and actually get a serial port emulator and send these codes. You could type them out to the plotter. You could technically, by the way, do this to anything that has a proprietary language. You could probably do it with a laser cutter if it weren't for the laser cutter protocols being proprietary and sort of the language of this stuff being like a secret. But regardless, HPGL, this protocol, is obsolete. People didn't use it, it went away. So there's no drivers now that, what a driver would do is take information like a AutoCAD drawing or something, take what it knew about the scale, took what it knew about the plotter's page dimension, and generate this code for you. And this is still what happens when you print a PDF. The protocols just look much more complicated than this, and there's much more rendering that takes place in the memory of the plotter itself. This plotter has very little memory. It does it the moment that you tell it to do it. So it requires quite a bit of coding. So the Chipotle people have made, and this is another nice thing about programming in Python or programming in general, is that the authorship question remains, but when you're leveraging another author at a different scale, that becomes very transparent and purposeful, and it becomes possible to be co-authors and abstract sets of code for other people to use. But I encourage you to go to chipotle.org and They're based out of the Columbia Music Project. They do very interesting computational stuff. So here's a plotter drawing. This one is used for calibration purposes. So its purpose is to take a pen that's a known age over here and draw very fine, short lines, give a little bit of spacing, draw fine lines again, give a little bit of more spacing, as it goes, drawing lines that are longer. And you can see the way that the pen deteriorates. There are places here where no matter how close you are to the paper, you can't see any individual line. So there's actually a scale at which the resolution of the movement of the pen's motors is finer than the resolution that you can see because of the physical properties of the ink. So I'm going to show you drawings that I have made with this pen plotter and precede them with some diagrams. So this is just the key for the diagrams. Things that are animate or that you're seeing a capture for just a moment are framed. Things that are fixed are filled in. Things that are computed but not drawn are a dashed line, and things that correspond to marks made on paper are a hard line. So here's the first set. The computed structure starts with a grid. It begins a line on that grid towards a focal point, truncates that line based on a given length, and repeats that for more than one grid. The algorithm couldn't be simpler, but when playing that out over a very fine scale of the pen plotter, you get a whole emergent set of qualities. There are, for example, no green pens in this drawing, just red, blue, and yellow. So, things like these striated marks are totally the result of the resonance of slight imperfections and slight misalignments of the motors in different directions. Here is another. Given points on a circle, starting a line from the center point that travels along, given a gradual curving trajectory, travels along and increases the extreme of its curvature to avoid intersections with it at the next step. So this is, again, not very complex, but requires a notion of time to be built into the line. The line has to know what might happen next, and if that thing were to happen, how might I steer away to avoid that intersection. And there are certain points where it has to steer and make a hard corner. And what happens afterwards is that coarse line is articulated with a finer curvilinear line, which is used to make these striated marks towards a focal point, which themselves are prohibited from intersecting this line. Fancy way of saying I made this. That focal point as a kind of depth cue is super important, and the ability to calibrate the line and the computation to get things like the lines being just barely visible as separate lines here and blending together here matters a lot. This happens to be the drawing that you saw the plotter making in the demonstration video. Another related one starts with a line that has a direction. That line repeats until it meets a boundary, and then another set is made, and the intersections are not allowed. However, so this is basically making these sets of things. One of the beautiful things about plotting is that you can make very intricate and delicate hatch lines that have the fineness of an etching. One of the problems with hatching, and one of the reasons why, like when you just do a fill with a AutoCAD hatch, and why if I saw that in studio, I'd be like, get that hatch out of here, it has nothing to do with your drawing, is it's just an arbitrary fill. But I get very interested if the hash could be programmed, and the hash was very much related to the shape and the boundary that it was in. All of a sudden the hash gets to be something that's quite exciting, where a hash could be a collection of lines, could be a material, it starts to have material properties. You'll see here, this is an animation that documents the building of this process, because that last diagram didn't quite do it justice, because what's not allowed to overlap was not the boundary of lines, but the lines themselves. So some of these lines, because their angles are slightly different, can nest themselves into other sets of lines. This starts to be not as straightforward as a non-intersecting boundary condition. And you get, that overlap leads to kind of different readings of, I like to read them as, surfaces that might start to suggest bending or folding in different directions. So this is another line that is made up of sets of sublines. So again, it's a dash line. This is a dash line. So the dash line where, like the hatching, the dashes are part of its DNA. So it's not allowed to intersect with itself, but if itself has left a hole, so the dash actually operates as a physical property. It can pass through that dash line. So it can actually go on for quite a long time, because there's always a possibility where it can steer and go through it a little gap. To ensure that it can go on for a very, very, very long time, and I mean days, that it can also, when necessary, shorten its length. So this is a line that also changes its nature from the start to the end. At the beginning, each segment is very strong, a polyline in AutoCAD. By the end, it's a very finicky, delicate curve, because the boundary conditions that have been made by its own kind of tail and path are restricting it. So here's another animation that sort of shows that. This is one of the ones that computed for a very, very long time. So the image, this video will skip forward quite a bit. You'll see that it gets smaller. Oh, and it also, this is another one of the interesting problems/opportunities of the pen plotter, is you can't do gradients. So the first thing that you would want to do, of course, is make a gradient. That's our nature. The thing that it can't do should be the thing that you try to make it do. So one of the things that you can approximate a gradient with is by having enough parts of the thing, you can increase the likelihood that the part of a thing would be a certain color. So in the beginning, there's a near 100%, 99.99% chance that the line segment will be green. Over the course of the line, that percentage gets lower and lower until it's more likely that the line segment will be blue, which leads to drawings that look like this. This is a tricky one because it needs many, many hours to run, but it is in some sense totally expected. But on the local, this one and the next one look as a type very, very similar. But the local conditions are totally subject to chance. So the fact that this one got more dense at this edge, part of the reason for the sphere, by the way, is to reduce the likelihood of corners, which would tend to get things, line would get stuck in. Here's another one where the parameters are slightly different. The gaps are a little bit larger here, so it tends to get stuck a little bit less. But another thing that can happen, besides the colors blending, is that the quality of the paper can change. So a line that's drawn on top of another line will affect the pen in a more abrasive way than drawing on an empty sheet of paper would. So, and likewise, the quality of paper changes depending on the number of lines. If this was an image that I did file print with, all of that information, the overlay would be reduced to or resolved to a color value that would then be printed out. Here, that resolution is a material condition, something not usual with computing output. So it's possible that the paper can rip or tear or become so saturated that it becomes black. They get more exciting. I'm presenting these in a kind of order of the complexity and the layers of structure that are necessary in the algorithm itself. Here is a lattice system that is defined initially with a boundary condition. So all of these lattice lines are on that fall within this boundary condition. And it follows a series of rules that are made to simulate the diffusion of particles, diffusion of fluids or diffusion of gases. There's a great explanation of this. This is a representation of a diagram that exists in Neil Gershenfeld's book, The Nature of Mathematical Modeling. I didn't invent this algorithm, but basically it relies on, if you think of the computing problem of trying to simulate a particle, it's extremely difficult if you're trying to simulate the flow of water by resolving molecules of water or individual particles of water. It becomes computationally very intensive, and therefore the performance would be very slow. What happens here is that the actual, it's not the diffusion of particles that are represented, it's the diffusion of states at these intersections. So to calculate this here, this would be considered on, because it has 5 values of on near it. So it has an on value of 5, whereas this point has an on value of 0. This one has an on value of 3, this one has an on value of 6. And the algorithm simply looks at each point in the lattice and looks at whether it has any special conditions, and if it does, do some rotations of the information along that lattice. Otherwise, rotate the information on that lattice. So there's a approximate conservation, or there's a conservation of on and off particles over time, but it's not actually simulating a particle moving from here to there. To make the drawing, there is, after this goes a certain number of steps, those values, the 5 on, the 3 on, the 2 on, are translated into a direction and length of a mark, which is then plotted. But before we get to the drawing, so here's a lattice, they're called lattice gas algorithms. Here is one diffusing, and so it's certainly, you can see the beginning of the diffusion happening here. If you give it a regularized input, a square, for example, it retains the square in a really awkward way. It's like imagining a perfect jello mold of red water existing in a pool of clear water, and there were no external forces on it whatsoever. And it only diffused when it sort of touched other pieces of water. You can run these, this is a video, but it basically runs in real time. This is it a little bit later, and then much later. A fascinating kind of mix of articulating form. Like this is many hundreds of steps later, and you can still see the edges of that square. But it has been diffused to a pretty significant extent. When that diffusion is also coupled with a plotter which is on the edge of its life. In certain lines, at certain times, at certain positions of the paper, it has a very difficulty eking out a line. So when the diffusion or of the algorithm is positioned on top of the depth of the pen, it becomes an interesting way to document time on different scopes and different scales in one drawing. So this is after just a few steps of diffusion. This is after many steps of diffusion. This is capturing one of the problems in one of the reasons why you don't see diffusion algorithms used. If you talk to someone in computer science, or especially mathematics who does computing, you say, do you learn about diffusion algorithms? They say, oh yeah, of course, it's a given. It's not anything special. It's like, do we know about a certain type of detail, or an axonometric drawing? But it's so one of the reasons why even those of us who do computing and architecture don't kind of come across that is it's set up to represent something over time. Its accuracy as a model doesn't have anything to do with a snapshot. It has to do with its performance as it degrades. So it's something that's very arbitrary to stop. So that's something that the pen plotter was uniquely suited to convey and not arbitrarily stop into an image, but make a drawing that also had the capacity to show time. So in this case, it's a couple of layers that represent the duration of diffusion stacked on top of each other. Another agent-based algorithm is Craig Reynolds, who went on to do, I think he moved on to Pixar. He developed some algorithms to simulate flocks of things. Pixar wanted to use him to do flocks of people and things in crowds that didn't need to be represented in detail, but their collective performance that needed to look natural. So he developed an algorithm for this thing that he called a Boyd, which is like a generic animal agent thing that has a very primitive behavior to tend to flock. So it looks in its sort of vicinity of what it can see and steers to match the direction that its neighbors are going. It also steers to match the average position of its neighbors. But if a neighbor is really close, it steers really dramatically to avoid a collision at all costs. So I have a grid. I have Boyds that start on the grid, travel off the grid based on these rules, but that are then resorted based on their position. That resorting first in the x direction and then the y direction leads to these lines, which then leads to these points, which are then used to draw lines. So here are just the Boyds. Here are just the Boyds with their lines. Here are just the Boyds with the lines and the interpolated lines in between. Here is state 1, state 40, state 50, state 90, state 120, or something like that. So now I want us to take a moment, and maybe you have this also, where you can, you're happy to take a moment to go into the world of drawing, or it's no problem if you want to say that these are artistic experiments. But there's a sort of tension when things are not overtly architecture. And yeah, I definitely have that. And there's definitely a, if there were to be a part 2 of this lecture, it would be something like the formal implications of this now. But one of the things I make a great effort to do is not to assume that these drawings should be translated immediately into architecture. So a couple of the very primitive, admittedly, next steps have been first to look at what is the other direction. How would you go from something like a sphere to articulate it with a drawing? So that's what all of these 4 are doing. Some of them are perspectives. Some of them are orthographic projections. This one is neither of those, but ways of taking 3D information, translating it into linear information that is specifically tied to the language and the mechanism of the plotter. The same type of thing for, I pick a sphere, I pick a hyperboloid, because they're sufficiently generic and neutral, even more generic from an architectural point of view than something like a cube, which already has edges and corners. And then the other thing is I do this kind of absurd thing where I'm interested in rendering or making the drawings. And this is a way, if you're rendering or making something that exists over time, or exists in 3D, if not 4D, it's a way to say, to keep things temporal and to avoid the commitment, or avoid the need to, or avoid the potential for things being lost in translation. So I have a series of things that do diffusion over the course of a sphere that are meant to be studied as very sort of short nuggets of things transforming. These are almost so fast that you can't see the thing, but you only see the transition of thing. This is, again, I think, hopefully, this is totally undercooked and underdeveloped. This is sort of like the trajectory that I'm on right now. aiming towards thinking about these things that might key into a very specific way of conceiving an architecture without having to be made into a model that becomes a simulation of architecture. So I will end with this. This is the first plotter drawing in my series that simply draws straight lines until the pen expires. It took like five sheets. It starts really a crisp, nice, thin line. It degrades and actually gets a little bit thicker and darker and then dies. So this is my A000000 drawing. Thanks. And I want the questions. Yes, July.
That's fascinating work. Does it make sense, and complete ignorance question, does it make sense to make your own plotter in order to reach boundaries?
Yeah, that's a very good question. So there's a whole slew of drawing apparatuses that are made by hand. So yeah, I've thought about this. Would it be valid for me to control the entire mechanism? And I guess my cop-out for the moment is that I'm fine with the found plotter as long as there is territory to be continually surprising in this, and it's far enough removed from the thing that you would get when you did file print to sustain me. So I guess if I had a student who said, I wanted to make my own plotter, does that align with your interest? I would say absolutely. But am I going to be making a plotter soon? I would say no, because I'm more interested in going into the qualities that make here and then reining it back to sort of tease out what are the architectural implications. So I think for me the pendulum is going to swing more back towards the core of architecture. But it does make sense. I mean, it also technically makes sense to have it to be, if you were a purist about it, I would be programming my own library to generate the HPGL code. So I can look at the Chipotle guys, the Columbia guys' code and understand exactly what it does. So there's no kind of lack of control there. But there's also something very pure about, okay, if I'm going to name and systematize, catalog all the outputs, I should go all the way back, and I should be writing the code and building the plotter. But then the problem is, what do you build the plotter out of? And even if I read it in pure Python, somebody wrote the Python interpreter. So there's kind of a never-ending pit on the other end of things. So I guess to be in computation, you can kind of never be a purist. You're always standing on the shoulders of somebody. You just have to pick where you're comfortable, where you want to end. But yeah, totally legitimate question.
I have a question that I didn't understand.
Okay.
It seems to me that there is a part of your work that is fundamentally programming, and another one that is, I will call it, for lack of a more sophisticated word, material.
Yeah. Okay.
Which has to do. You could be doing all of this work on a printer. You could.
Couldn't.
You could.
Could.
Why couldn't? And that's what I don't understand.
Okay, so I can answer your why couldn't you do it on a printer question, but I follow up, please, because I'm not sure that I understand what that has to do with the material question. So, to me, I prefer the question of material to be present in the computation, right? The digital project relied on the fact that you could conceive of forms independently of their construction. So a post-digital project will be really interconnected to methods of making and material and construction. Not to say that all digital projects weren't. So I care about material, but I also care about how does the material permeate into the things like writing code. So the place where you can find the closest potential marriage between the material and the code is in the drawing. And that's why the drawing matter. It's important that these are drawings and not images, because when they're drawings, the line matters as a material, and so it becomes potential. Not that it always has to be an analog of a built material, but it can perform that way, right? You're dealing with affecting the material of the paper. So there's always the potential to kind of dip into material territory in the drawing itself. So that's why if this was a printed image, it would look, depending on the resolution, either every line exactly identical or probably just gray bands. And you can look when these are printed in person, you get all sorts of qualities that are totally inherent to the materiality of the felt of the pen plotter head and the paper. Does that sort of answer? So basically, there's not an obvious answer where by being plotted it gets you something in particular. It just sort of sets up these material things being in the same place. So here's another example. If I could
my question is, I mean, I'm following you, but the question is a lot simpler.
Okay.
Are these two tracks of research that seem to happily come together, or they are intrinsically linked? Doing it with a plotter and programming.
I think I can make a case for them being intrinsically linked, but the way they happened was that they are, I was kind of curious about a plotter. I have this sad story about when I was in my MR program, there was a plotter that I never got to use and thrown out. I missed the plotter, and I had a elevation drawing that was so detailed that it was the print plotter was running out of memory, so I needed it, and so I was doing computation at the time that was about making a really pedestrian, like moving facade, and so it was odd that I had these interests and couldn't output the image, and so the plotter was going to be like a hobby that turned into something that could be an outlet for programming, to get at, because I care about how the programming, in its most primitive sense, can be manifest. So the moving and controlling a line, I'm kind of happy and content that it's the most primitive way that you can do programming and get something out. There's few stuff in between, and get something out that we can use and think about as architects. But yeah, the honest answer is that there wasn't a need for a plotter. There was like an interest in a plotter. Yes?
Carl, I'm always fascinated by how one begins a certain kind of research. And I like that story because it talks about frustration that led you to this research. So the question I have for you would be, what do you think is missing in our education as an architect, like educating future architects, that based on your research, you can change?
Yeah, okay.
And so that question is not so much loaded, but I appreciate the fact that you're separating this into making a translation to architecture, because a lot of the problems that we're seeing, if you want to call it computation architecture, before it's called algorithmic architecture, is that translation always somehow fails. And so, based on your research, what would you change or add?
Yeah, okay. So the best questions are the hardest to answer. So if you look at curricula, there's never a place for computation theory, right? So the first place is that there has to be a kind of a safe zone where you can do computation and explore computation in a way that does not need to be applied to a project, given the project's terms. So that's one of the reasons why my story is kind of sad, is that there was like in my MArch, there was a plotter sitting next to me the whole time, but there was never an opportunity for me to take a road that diverged from the project and explore it. And so I guess if I step back a little bit further, I guess I would kind of love for everyone to be able to take the Computer Science 101 class. And some universities have a kind of generic, the way architecture has a course, some schools for non-architects, computer science departments have courses for non-computer scientists, and that can certainly be of value. But one thing that does kind of haunt me is, if this stuff is really going to affect architecture, shouldn't it be present at the foundational levels of a design curriculum? And so the unavoidable answer is yes, but then you have to face the fact that doing this kind of stuff takes a lot of time and energy to like strip away all of the conveniences of software, which are also convenient for learning software. So my sense is that you don't have to be a purist about this, but you don't also want to have a architectural education relegated to a bunch of how-to situations. Like drawing, like every medium or every process, we have a capacity to critique the process as much as we have the capacity to critique the results. So I guess and no one has asked me the question about culture, like why I'm calling this computing culture and not talking about computing methodology or computing process exclusively. Part of it is just like kind of a mindset of not accepting something that comes as an output as a given, right? So always having a built-in capacity to take what was a black box of something like a tool or something like that and either remaking it or undermining it or misusing it to the point that you can work your way backwards from user to author. I think you can tell from the fact that I answered this question in like 3 little mini parts that I think this is a hard question. And anybody who answers that question with a straight answer, I think isn't doing justice to the complexities of computation. So yeah, that's where I stand in a kind of messy, semi-articulate way. But here's the other thing. So it's also a really hard question because technology is the very thing that is going to change fast and does change fast. So like it becomes very, very difficult to develop a core of a curriculum that responds to computation in its current state without, by definition, becoming obsolete or missing some kind of important breakthrough or something. So yeah, I'm content, I guess, that I answered this question fairly. But yeah, I'll take that question anytime, and I'm glad that the question is on the table. Yes?
So the digital projects that you showed as a kind of introduction to what you're not going to talk about, do you think that those projects, were they doing computation or were they doing computerization?
Yeah, that's Greg, right? Hi, Greg. Thanks for coming. It's a mix. And I'm hesitant to get into like a critique of digital one person versus digital another person. But in a lot of places, yes. In a lot of places, no. And even when the answer is no, there can be some very exciting and paradigm-shifting ways of modeling, for example, now that you can surface model. I mean, Frank Gehry is a good example of that. He is not a digital person. He is not writing the code, but they're kind of Bilbao and post-Bilbao are different specifically because of computation is there as a way of fabricating and constructing, managing, resolving those kind of issues. So it's Bilbao is a digital project without the computation needing to permeate to the design, and that's okay. There are some digital projects that look at new kind of topologies that can only be created or only are the result of kind of flaws or quirks in algorithms. So those are more like quintessentially digital in the sense that the form is a digital artifact. And in that case, it's a computed artifact, even still. So, but yeah, I think that's a good question. One of the things that's when you see a contemporary this is one of the filters I use in the studio, is if I see a student project that looks like those projects but doesn't act like those projects, it's a huge, huge problem. There's a lot of, I don't want to go there because it'll sound too mean, but that becomes a big problem, and I'm sympathetic to it also because those projects looked different, so they're easy to copy. They're easy to treat as a kind of new topological or formal condition, but that really undermines any potential for them being a kind of different level of operation. Yes?
I'm interested if you can go a little bit beyond the scope of what you talked about.
Okay, try.
You made references to sort of projected connection to architecture from the drawings.
Yeah.
And you also talked a lot about a plotter on the edge of its life, or you've named these things rational names. And there's a degree of life that we see in these drawings that, at least for me, is much more evocative in the things that you showed of your own and also the precedents than the average drawing printed off a conventional plotter that we use.
Yeah.
And so I'm wondering if you can make some connections to this life, or if you can expand on that a little bit, and the way that we connect to these machines and may in the future.
Yeah. Well, that sounds, if you have ideas about that, I would love to hear them, because that is, I don't immediately have a way to do that, and part of the ways, there's a certain need to not be delusional about the fact that this life is an artificial life, so to sort of treat it as a kind of thing to nurture is kind of inappropriate, right? But at the same time, as a kind of self-evaluation, I think it's fair to acknowledge that my tendency is to treat them that way. So to be honest, I never really thought about that aspect as a thing that would carry forward. Other than I would say we naturally say that buildings have a life, and a building is dying, or is this building dead, or is that city dead, So I think there is something to the controlling deterioration and designing with the dimension of time being present that I can tell you that I value. Whether there's a way to connect that to what I have now, it's too separate for me to be able to do in an honest way, other than to say I take that as kind of valid of a question, and I would support I feel like if you were to do that, I would say, yeah, let's talk about this and find a way to do that, but it's not sort of where I expect to go. Of course, where I expect to go is not where I will go. But one thing I would say as a kind of necessary, honest step would be to look at things like, this is about lines that have multiple readings, right? Fundamentally, that's what gives these drawings life. So I would find it necessary to articulate an architecture of lines with the same kind of ambiguity or dualism or kind of potential to, in their degrading, make new lines. So this is why I guess I would say if you and I were to kind of go on this path to get this living, energetic, dynamic architecture that dies in a kind of graceful and elegant and profound way like these drawings, we would need to first explore how they would do things like make a corner or make an edge or make a wall first, so that the lines, it wouldn't be a metaphorical connection. It would be an actual, in the language of architecture, connection. So that's where I would go if that was my trajectory. These are good questions.
I have a question. Yeah. Kind of going back to what Gabrielle was talking about. There's this idea that, for me, this is, I call it computer-aided drafting. So it's taking the drafting out of the drafting pen, and currently we use AutoCAD, which is sort of the drawing out of the artist's the resolution of the plotters we use today, right, versus of the past.
Yeah.
At some point, we'll probably get to the quality of being able to produce this. So wouldn't that just become another step of programming to create this? And sort of how do you feel about the ongoing technological advances?
Yeah, that's quite, I mean, I think your question is a lot similar to Lai's question, which is, kind of imagining or seeing that this fits in a kind of sweet spot of kind of things that are imperfect and the capacity to control them. And Lai's question was seeing that I have control over a certain segment of things, and yet that control is broader or different than what we're normally used to, but it's still a segment. And so I think I'll answer your question the same way, which is, if you push forward, there's eventually a paradigm where you're fabricating at the level of the atom, and so every kind of given that has to do with a medium is potentially obsolete. And so I guess what I would say to that is there's always this idea of a sweet spot, or where things are flawed or weak or not possible right now is the space to focus on. So I don't think that in particular these drawings are better than a drawing that would be using if you could imagine if you had a perfect control of a dot matrix printer or an inkjet plotter, if you could control it, you could do all sorts of beautiful things like this. It's just that the plotter right now is totally controllable on the level of how it operates. So I think that it's totally just this process, this culture of being able to identify what you can't control, attempting to control it, and then testing the implications of it that matters to you. Chen?
I have a question about what you will see what the future gonna lie. I mean, the first time I see a computer is with a screen. I had never seen a computer without a screen before. And the first drawing software I used to is the log software. It's like a vector tracing software to tell a small turtle to move around the screen and draw lines out. And then as time goes by, as I enter high schools and university now, software is getting more complicated, and now Photoshop comes out and the Rhino comes out. It seems to be that the direction is going that computer scientists or programmers trying to make the software mimicking what can be actually created in real life.
Yeah.
And my question is, somehow that to me is lost, it has lost the original digital culture, as you talk about, when I type in my programs and drawing lines with Small Turtle.
Yeah.
So my question to you is what would you imagine the future gonna be? Do you imagine that people will focus more on the basic of a digital culture or on the simulation in the digital domain of the real world? Because in today's Rhino, if you want to create a tetrahedron, it's actually quite difficult, because in a real life you can just put several triangles and put them together with glue and it will create a tetrahedron. But in the digital domain, you have to rotate, you have to try to figure the angle out. Do you imagine in the later on future that there will be the step that somehow you can simulate the hands, putting two triangles together in a digital domain? And do you see that as a beneficial way of going, or is it a detrimental way of going, as things get easier and easier and we lost the digital culture background?
Yeah, I mean, it's quite an interesting question. I mean, one of the things first to note is that technology for architecture is not influenced by architecture. I mean, you could look at the market share of even Autodesk. The percentage of people who use it that are in architecture is so minuscule. They're not designing for architects. Those computers that we use are not designed for it to even do design. As a byproduct, you can make them do design in them. But the trends are much of our personal computers are much more broad and much more about lifestyle decisions and our access to information. So that's first, but that doesn't really answer your question. I mean, I guess you could say most recently there are trends to take the computer out of being a thing and take the computing, this is clouds and stuff like that, put it elsewhere, and so the information that comes to us might not be in a box or on a screen, but would be augmented here or in our space. So it's kind of like what you're proposing, but I could see a future where it's not going towards being more real in the virtual space of here, but taking computation and merging it with our actually real space. And I think no matter what, it will be tending towards the three-dimensional, the model, or if it's not a model, interacting with real things. All sorts of great technology that can do things like perceive depth based on motion cues super fast. It's opening up the possibility of not a lag or delay between how things are computed and what we see and can touch. And I'm not opposed to that or in any fashion. I like that stuff. I would want to use that stuff. But I do think that there's something to the drawing as a reductive space that potentially shows the relationship between two systems on two axes that is wired to how we think, that helps us resolve things in an important and abstract way. Maybe it's possible that two-dimensional kind of hard wiring to our brain is also a result of the images around us that have been predominantly two-dimensional. I'm not sure, and I'm not an expert about that, but I think probably computation will have to be a kind of pluralistic agenda, and it would not be possible to say that I've got to do pure computation to get down into the lowest levels of computers and leave out advancements in personal computer technology. So I see it going a little bit of both. One thing that I would like to put my foot down about is that architecture needs computation. There needs to be a place in architecture where we do computation, rather than a place where architects use the computation or are consulted by experts who are making or controlling the computation. Question in the back. Is that Camila?
Yes.
Hi.
Hi. So, sort of
Can I suggest that this is the last
Yeah,
question?
that's good.
And then there could be a bevy of questions around.
Okay.
So I just want to piggyback on the last thing that you just said and
Yeah.
see if you had anything else to add to that process of translation between the programming and the architecture, and how do you compare and contrast this translation and being true and honest to the original code that it generated? So I guess the question is, how do you
Yeah.
compare the programming towards the architecture, and where do you see this translation being true to the original intent of what you're coding?
Yeah. Okay. Again, it's the first of all, I agree with the premise of your question, and I think that your question is like an important question that everyone who does computation should be ready to ask, should be regularly asking themselves. So the question of translation for me is inevitable, and so there's two kinds of translation. There's translating the result of the code, and then there's translating the code. And one of the shortcomings with something like scripting as opposed to programming is that scripting inside a bubble of something like software it prescribes a domain in which you can operate. So it becomes very difficult to transition from evolve your program from a program of interactive lines to a program of interactive surfaces to a program that controls a robot for making. So I would try to be nimble about translating the algorithmic operations as opposed to translating the result. That's not always possible, and sometimes it's important to do the exact opposite. Acknowledge that when you're programming the relationships there are not related to architecture, and there's a time to make a clean break where we use our our powers of perceiving and interpreting and reading drawings to make a clean break between the programming. That's not to say also that programming has to stop then. You could make a program, give you some output, program the way you read the thing. But yeah, I guess, so that's a cop-out, but my answer to your question is that yes, we should keep answering that question. It's not always one way to answer it, but if you find yourself in a default, then I think it can be potentially a very bad situation. All right, thanks everybody.